Welcome to Oxpoon, the technology magazine. Hello and welcome. The whole world seems to be talking about heat pumps at the moment, so I thought I'd bring a heat pump with me today. I would almost say that this is perhaps the smallest heat pump in the world that we see here. On a more serious note, it's a good illustration of the way a heat pump works. A pump compresses gas. When we compress the gas, the pressure and temperature increase. In the case of the air pump, it is air, so our air mixture is also a gas. In the case of heat pumps, correspondingly, it is a refrigerant. But let's stick with air for now. I have a multimeter with a built-in thermal imaging camera on my desk here. When I switch to thermal imaging mode, we see a picture, a video recording. I can show it here using my hand as an example. So we can see the fingers, which are often cold in the winter. They are also shown here as colder. We have the legend on the right-hand side. We can see that the light yellow shades indicate a higher temperature. If I go over here to the ball of the hand, we can see that it has better blood circulation and is warmer. We can use this illustration to show that this smallest heat pump in the world can actually generate heat. I have brought the hose of the bike I rode as a kid for this purpose. I can connect the pump to the valve here. Once I've positioned the right area in front of the thermal imaging camera for the demonstration, I'll pump it up quickly, because the faster you inflate, the more it heats up. So we can see here that the metallic area of the air pump has heated up considerably compared to, for example, when we go into the dark area of the plastic. This is the effect I wanted to show you. By compressing the gas, by compressing the air, we have generated heat. I have prepared another experiment to illustrate the principles of gas theory, in concrete terms, the thermodynamic effects, in a slightly different way. The bicycle tire is taken aside, and I take out my small loudspeaker. My lunch is already prepared on the loudspeaker, so to speak. I've just been to the pantry and picked up some dried peas. And when I've finished the experiment, I can still benefit from its outcome. Connected to this speaker is any smartphone with a frequency generator, app. The sound generator produces a sine tone at a certain volume. And in our model here, this volume represents the temperature that prevails in the gas. And we can start the experiment, first with a slightly lower volume, and let's take a look at the peas. So we see the peas at a low temperature. They move due to the kinetic energy supplied, but they still move relatively slowly. If I now increase the volume, so that was 2 stages. We've seen that 1 pea has already found its way to the floor, so I'll have to hurry if I want to get my fill of them this lunchtime. So we can imagine the peas as the molecules of the gas, in this case air, and the higher the temperature, the more vehemently, the more violently these molecules move. And we have seen, and we can see it again, now that they are here, they need much less space than when they are in a higher energetic state. And that's the reason why the gases expand. We don't normally see that. These are microscopic effects. We can perceive the temperature through our skin, for example, but we can't see these microscopic effects, these dancing molecules, unless we use appropriate measuring equipment. So we now know that the movement of molecules corresponds to the temperature as we perceive it. And then I would suggest we move on from the main course to dessert. I've brought a refrigerator here, or rather another simple model of a refrigerator, but a fully fledged functioning refrigerator. And we can open it. And yes, there was a P in the way. And we can see that the temperature in the fridge is currently 1.4 degrees plus Celsius. And the dessert is already in the lower shelf. This fridge is also a heat pump. Whether we're talking about cooling or heating is a matter of perspective, because the point here is that we are cooling inside. But this cooling effect works by dissipating heat to the outside. And in large kitchen fridges, as we know them, we normally have a grid at the back, a cooling grid, which then dissipates this heat well into the room. In this case, of course, everything is much simpler. But we can also take another look at this with our thermal imaging camera. So I'll put the main dish aside for now. And if I go into the area at the back here with the thermal imaging camera, we can see that it's a bit difficult because the grid is in front here. We can't measure it properly, but at least we can get a temperature. H is hot, is the hottest point that is automatically filtered out here. We see a temperature of 26 degrees here. If you were to get up close and try and find the place in the grid where the hottest spot is, then we would get temperatures of well over 30 degrees. But we can also see here that we are above the ambient temperature. So this refrigerator here is a heat pump. It emits warm air from the inside to the outside, cooling the interior. And this is also how the large kitchen fridges we have work. And conversely, this is also how the modern heating systems that are installed in large numbers in houses these days work. Now we have worked with air in our example. We remember the air pump, which I introduced to you as a heat pump. But modern actual heat pumps of all kinds use coolants. These are certain materials that have a boiling point below that of water. And this coolant is circulated. It is made gaseous, transfers the heat to the heating or cooling system via a heat exchanger, cools down again, becomes liquid again, and receives air from outside, ambient air, which is warmer than the cold state in which this coolant then finds itself because it has been expanded. We have just said that when we compress gas, it heats up. When we expand gas, it becomes colder. And this effect is exploited, for example, in a heat pump that works with ambient air, so that heat can be extracted from this ambient air, even though this ambient air is much colder than the air we have inside the house that we want to use to heat our home. So this is a very sophisticated principle, and we usually achieve a factor of 3 or 4 in real-life examples compared to purely energy-efficient, purely electric heating. Anyone who maintains or checks coolant systems, heat pumps and similar systems, or is possibly looking for faults, must always have a measuring device with them that is handy, and at the same time fulfills all the functions required to carry out maintenance work. And this is where the PCE-HVAC 10 comes in handy. We can see the connections below. These are 7/16" UNF connections, as are often used in heat pumps. And corresponding connection hoses are also supplied to integrate the device into the coolant circuit. When we take a look at the display, we can see at the top center here that we have set a specific coolant. This device can process a total of 18 different coolants, or work with 18 different coolants. I can go into the settings mode, and we can switch through here. Or I can even hold down the key, and we can see how the different agents are switched through. I'm not going to try all 18 now. I think you'll believe me that this is possible. 2 PTC temperature sensors are also supplied, which are connected to the hoses, with these clamps here, which can be opened and attached to the corresponding infrastructure. And the temperatures are also shown at the bottom of the display. Determining the temperature is of course important as a correction factor for the pressure. This device works at pressures from -1 to 60 bar, can also be switched between different units, and works at temperatures from -10 to +200 degrees Celsius. A small special feature here is the control window at the bottom. This means that once we have inserted the device into the coolant circuit, we can visually check the coolant flow there. All in all, the PCE-HVAC 10 is an excellent and handy assembly aid for anyone who works with heat pumps and coolants. When it comes to replacing coolant, whether for repairs or when it needs to be replaced at regular intervals, you need a vacuum pump. And I have brought along the PCE-RVP 180. This is a vacuum pump that can extract 226 liters per minute. So it's a vacuum pump for really large systems. And let's take a look at the nameplate here. It says at the bottom that it has 3/4 horsepower, or 550 watts. So it's a pretty big one. We can only run it here in the studio, because we can't and aren't allowed to work with refrigerants in the studio. We can only run it for a short demonstration, in a dry state so to speak, and hear that it starts up and makes noise. I'm doing that right now. It is a vacuum pump that is oil operated, and we can look at the side here, so we can see a very large and clear window here, in which we can keep a constant eye on the oil level. And if we look up here, on the top side here, is the filler neck. The corresponding threads are also supplied, which we can use to top up the oil. The connection to the coolant circuit is made via 1/4 inch or 3/4 inch SAE threads, which we can see in the picture above. All in all, a very nice powerful vacuum pump, the PCE-RVP 180. I am standing behind the PCE-RRU 10. This is a recovery device for refrigerant. In other words, for cases in which the refrigerant is not yet to be replaced, but is to be refilled into the original system after maintenance or repair. In a way, this device has it all, because it offers some nice, elegant functions. For example, it has this practical carrying handle, which makes it easy to transport to the system. But it also works completely oil-free. There's a 2-piston compressor in here that doesn't need any oil, so there's no risk of oil potentially flowing back into the coolant circuit. And it has a self-cleaning function. I can turn the device a bit towards the camera. So we have purge down here. For example, this device is able to clean itself of the coolant that is run through here after use. We can see the connections here at the front. It's a 1/4 inch SAE thread. Here on the side, we have the connection for the cable for the limit value transmitter on the coolant tank. Because at a pressure of approximately 38.5, the device switches off automatically, so that it is not damaged, and so that the tank is not damaged. Not only does it switch off, but it can also display the pressure. We can take a look at the display here. It's really easy to read. It's very large and clear. And we can also see that we can switch over. So here we have PSI and bar and other units. So there is a lot of flexibility here. It works with Class A1, A2L, and A2 refrigerants, and can transport up to 9.5 kilograms per minute, depending on the refrigerant in question. This filter and a short connection hose are also included in the scope of delivery. All in all, the PCE-RRU 10 is a well-designed, well-thought-out device for professional maintenance. Let's take another look at the devices in the overview. First, the technician's aid, the mobile device that we can bring with us for maintenance and repairs. The PCE-HVAC 10, with an easy-to-read display and a wide measurement range. Then we have the vacuum pump when we need to replace the coolant. when we need to extract the coolant. The PCE-RVP 180 vacuum pump with a flow rate of 226 liters per minute, also suitable for very large systems. And last but not least, the PCE-RRU 10. A really well thought out device when it comes to recovering and reusing the refrigerant. An oil-free 2-piston motor and a good device for professional use. See you next time and goodbye.
Discover and order the latest measuring and test equipment now on www.pce-instruments.com.